Section 3.3, we'll be talking about diagonalization. Our goal, given a matrix A, a square matrix, I want to construct a basis B for Rn so that the matrix A, but in the basis B, is a diagonal matrix. So that means that if you take the linear transformation T of A and you turn it into a matrix using the basis B, you get a diagonal matrix. All right, let's start with similar matrices. Let's start slowly. Section 3.3.1, similar matrices. Here's a definition. Let A and B be n by n matrices. A and B are called similar matrices whenever there exists an invertible matrix P so that B is P inverse AP. We then write A tilde B. All right, one thing that's nice is if you have similar matrices A and B, then their corresponding linear transformation, those represent the same linear transformation, except that you're changing bases up to the change of bases corresponding to the matrix B. All right, so really we're trying to figure out when two matrices represent more or less the same linear transformation. So the same linear transformation up to a change of basis. All right, so let's start by looking at what similar matrices the similarity has as a characteristic. So similarity of matrices gives an equivalence relation on square matrices. That's the best type of relationship between objects. So what it means is that a matrix A is always similar to itself. If A is similar to B, then B is similar to A. And then if A is similar to B and B is similar to C, then A is similar to C. All right, so let's prove that. I want to take any square matrix A. I'm going to take P, the identity matrix. Then if I look at at P inverse AP, the inverse of the identity is the identity. And so I get A back. So that means A is similar to A. The second one, I'll leave it for you in the worksheet or the assignment. Now, in part 3, assume that we have a B similar to C, so that means B is equal to P inverse AP, and that B is similar to C, that means C is, well, for another matrix, so Q inverse BQ, I want to show that A is similar to C. So that means I need to try to write C as a product with A in the center. So I know C is Q inverse BQ, and then I also know that B is P inverse AP, and then I could reshuffle this. That's Q inverse P inverse A PQ, and then I have PQ inverse A PQ. So yes, A is similar to C. All right, so the reason why equivalence relation is so important is they divide your set. So in this case, it divides the set of all n by n matrices into what are called equivalence classes. So this means that the n by n matrices are divided into equivalence classes in which all the matrices are similar. So every matrix similar to 1, 2, 0, 0 would be here. We'd like to understand these classes better. More precisely, we would hope to have clear criterion to determine whether two matrices are similar. Ideally, we would have a list of matrices so that every square matrix is similar to exactly one matrix in this list. That would translate to a full description of all types of linear maps in Rn. So understanding when two matrices are similar, that's the same thing as understanding what type of different linear maps you could have up to a change of basis, right? If it's the same map but with a different basis, I want to consider it the same type of linear map. All right, so let's start in our quest of finding conditions on matrices that ensure they're similar or that ensures they're not. Let's look at this first example. Consider the matrices. I have A here and I have B here. I want to show that the matrices A and B are similar. It's hard to find P in general. We'll find how to do it later on, but Maple gave me this P. All right, so I want to see what happens when I multiply B by P inverse and P. I want to show that that's A again. All right, so P inverse, 1 over the determinant, that's 3/5. And then I switch the two and I flip the sign of the off-diagonal elements. All right, I want to multiply this by B. And then by P again. Well, I guess not again. It was P inverse before. All right, so let me simplify P inverse. That's going to give you 1, 0, 4/3, 5/3. And then let me multiply these right here. So I get -8 plus 80 over 5, that's 16. And then I get 0, that's -12, the 5 cancels. I get, I'm going to need more room probably here. I get 6 minus, so 6 minus 56 over 5, and then I get 42 over 5. All right, so I need to multiply 1, 0, 4/3, 5/3 by 8 minus 12. That's 30, so that's -26 over 5 and 42 over 5. So 8, that's fine, -12, that's fine. The bottom is a bit more work. I'm going to get 32. Let's put it over 3. Then here the 5 cancel, I get -26. And then here the 3 cancels, I'm going to get -48. And then here the 5 cancel and the 3 cancels as well. No, that's -16, sorry. -16. And then here the 5 cancel, the 3 cancel, plus 14. And so I do get 8 minus 12. Here it's 6 over 3, that's 2, and that's -2. And so this is A. All right, I want to find the characteristic polynomial. Let's do A first. I want to find the characteristic polynomials of A and B. Yeah, so let's do A first. That's 8 minus x minus 12, 2 minus 2 minus x. So that gives me 8 minus x minus 2 minus x plus 24. Let me put that here. And so I get x squared minus 8 plus 2, so minus 6x minus 16 plus 24. I get x squared minus 6x plus 8. All right, let's try the one for B. Don't hesitate to pause and try it for yourself. Then you can fast forward if you have the right answer. And so I get -8 minus x, 14 minus x plus 120. That gives me x squared, then minus 14 plus 8 minus 6x. And then I have minus 8, that's 32, 112 plus 120. I get x squared minus 6x plus 8. And so these similar matrices have the same characteristic polynomial. That's nice. And so they'll have the same eigenvalue since these are the zeros. Let's find a basis for each eigenspace of A, and we'll find a basis for each eigenspace of B and see what we can find. So for lambda, what are my lambdas? Oh, let's factor this. So x minus 4, x minus 2. So let's do lambda equals 2. My matrix would be 6 minus 12, 2 minus 4. That reduces nicely to 1 minus 2, 0, 0. I have S. And so I get x, y, x is 2s, y is s, so I get 2, 1s. So my basis for E to A, let's be precise because we have two matrices here, I don't want to get confused, is 2, 1. All right, lambda equals 4. I get 4 minus 12, that's a 2, and minus 4 here, that's minus 6. So it reduces to 1 minus 3. And so I have an S, xy equals 3ss. That's 3, 1s. And so my basis, E for A, is 3, 1. All right, so I want to see how this compares to the situation for B. I want to see if the eigenvectors for B are the same. So let's try lambda equals 2. What was B? I have it here. I just need to plug in 2 as x, so I get minus 10, minus 20, 6, 12. When I reduce this, I get exactly the same thing as above. Very cool. So xy would be 2ss again, so 2, 1s. So the base for E to B is 2, 1. Very nice. This is the same. Let's check lambda equals 4. For lambda equals 4, I would get minus 12, minus 20, 6, 10. That reduces to 1, 10 over 6, 5/3. Uh-oh, not the same. All right, so xy would be minus 5/3 1 times s, and you would get a basis, which is minus 5/3 1, and so these are different. So let's try to make this precise, but it doesn't appear like the eigenspaces match. Something's going on because these are the same, but these are different. So let's try to make this precise. All right, so in the next theorem, we'll actually state what it means for two matrices to be similar, what they share, what they have in common, how they're different, and then this situation will make more sense.